The simplest hydroxide derivative of benzene is phenol. It is its common name and also an accepted IUPAC name. As structure of phenol involves a benzene ring in its substituted compounds, the terms ortho 1,2 distributed, meta 1,3 distributed and para 1,4 distributed are often used in common names. Dihydroxy derivatives of benzene are known as 1,2, 1,3 and 1,4 benzenediol. Ethers. Common names of ethers are derived from names of alkyls aryl groups written as separate words in alphabetical order and adding word ether at the end. For example, CH3O C2H5 is ethyl methyl ether. Common and IUPAC name of some ethers. If both the alkyl groups are same, the prefix di is added before the alkyl group. For example, C2H5O C2H5 is diethyl ether. According to IUPAC system of nomenclature, ethers are regarded as hydrocarbon derivatives in which an hydrogen atom is replaced by an or OAR group, where R and AR represents alkyl and aryl groups respectively. The larger R group is chosen as parent hydrocarbon. The name of few ethers are given as example in 7.2 table. Structure and functional group 7.3. In alcohols, the oxygen of the OH group is attached to the carbon by a sigma bond formed by the overlap of sp3 hybridized orbital of carbon with the sp3 hybridized orbital of an oxygen. Figure 7.1 describes structural aspects of methanol, phenol and methoxymethane. The bond angle COH in alcohol is slightly less than the tetrahedral angle 109 degree 28 minutes. It is due to the repulsion between the unshared electrons pairs of oxygen. In phenols, OH group is attached to sp2 hybridized carbon of an aromatic ring. The carbon-oxygen bond length 136 picometer in phenol is slightly less than in methanol. This is due to, first, partial bond character on account of the conjugation of unshared electron pair of the oxygen with aromatic ring, and second, sp2 hybridized state of carbon to which oxygen is attached. In ethers, the 4 electron pairs, i.e. 2 bond pairs and 2 lone pairs of electrons on oxygen are arranged approximately in a tetrahedral arrangement. The oxygen bond angle is slightly greater than the tetrahedral angle due to the repulsive interaction between the two bulky R groups. The CO bond length 141 picometer is almost the same as in alcohols. Alcohols and phenols. First, preparation of alcohols. Alcohols are prepared by the following methods. From alkenes, by acid catalyzed hydration. Alkenes react with water in the presence of acid as catalyst to form alcohols. In case of unsymmetrical alkenes, the addition reaction takes place in accordance with Markovnikov's rules. Mechanism. The mechanism of the reaction involves the following 3 steps. Step 1. Protonation of alkene to form carbocation by electrophile attack of H3O positive. Step 2. Nucleophile attack of water on carbocation. Step 3. Deprotonation to form an alcohol. Second, by hydroboration oxidation. जो हाइड्रोबोरेशन ऑक्सीडेशन थी वो फर्स्ट रिपोर्टेड बाय H.C. Brown in 1959 for his studies on boron containing organ compounds. Diboron BH3 whole twice reacts with alkenes to give trialkyl boranes as addition product. This is oxidized to alcohols by hydrogen peroxide in the presence of aqueous sodium hydroxide. The addition of boron to the double bond takes place in such a manner that the boron atoms get attached to sp2 hydrocarbon carrying the greater number of hydrogen atoms. The alcohol so formed looks as if it has been formed by the addition of water to alkene in a way opposite to Markovnikov's rules. In this reaction, alcohol is obtained in excellent yield. Second, from carbonyl compounds by reduction of aldehydes and ketone. Aldehydes and ketone are reduced to the corresponding alcohols by addition of a hydrogen in presence of catalyst. Catalytic hydrogenation. The usual catalyst is a finely divided metal such as platinum, palladium, or nickel. It is also prepared by treating aldehydes and ketones with sodium borohydride NaBH4 or lithium aluminum hydride LiLH4. Aldehydes yield primary alcohol whereas ketones give secondary alcohols. By reduction of carboxylic acids and esters. Carboxylic acid are reduced to primary alcohols in excellent yields by lithium aluminum hydride, a strong reducing agent. However, LiLH4 is an expensive reagent and therefore used for preparing special chemicals only. Commercially, acids are reduced to alcohols by converting them to esters, followed by the reduction using hydrogen in the presence of catalyst. Third, from Grignard reagent, alcohols are produced by the reduction of Grignard reagent with aldehydes and ketones. The first step of the reaction is the nucleophilic addition of Grignard reagent to the carbonyl group to form an abduct. Hydrolysis of the abduct yields an alcohol. The overall reaction using different aldehydes and ketones are as follows. You will notice that the reaction produces a primary alcohol with methanol, a secondary alcohol with other aldehydes, and tertiary alcohol with ketones. Preparation of phenols. Phenols are also known as carboxylic acid, was first isolated in the early 19th century from coal tar. Nowadays, phenol is commercially produced synthetically. In the laboratory, phenols are prepared from benzene derivatives by any of the following method. First, from haloarenes. Chlorobenzene is fused with NaOH at 623 Kelvin and 320 atmospheric pressure. Phenol is obtained by acidification of sodium phenoxide, so produced. Second, from benzene sulfonic acid. Benzene is sulfonated with oleum and benzene sulfonic acid, so formed is converted to sodium phenoxide on heating with molten hydroxide. Acidification of the sodium salt gives phenol. Third, from diazonium salt. Diazonium salt is formed by treating an aromatic primary amine with nitrous acid NaNO2 plus HCl at 273 to 278 Kelvin. Diazonium salts are hydrolyzed to phenols by warming with water or by treating with dilute acids. Fourth, from cumin. Phenol is manufactured from hydrocarbon cumin. Cumin isopropyl benzene is oxidized in the presence of air to cumin hydroperoxide. It is converted to phenol and acetone by treating it with dilute acid. Acetone, a byproduct of this reaction, is also obtained in large quantities by methanol. By this method, physical properties. Alcohols and phenols consist of two parts, an alkyl aryl group and a hydroxyl group. The properties of alcohols and phenols are chiefly due to the hydroxyl groups. The nature of alkyl and aryl groups simply modify these properties. First, boiling point. The boiling point of alcohols and phenols increase with increase in the number of carbon atoms. Increase in van der Waals forces. In alcohols, the boiling point decrease with increase in branching in carbon chain because of decrease in van der Waals forces with decrease in surface area. The OH group in alcohols and phenols is involved in intermolecular hydrogen bonding as shown below. It is interesting to note that the points of alcohols and phenols are higher in comparison to the classes of compounds, namely hydrocarbons, ethers, haloalkenes, haloarenes of comparable molecular masses. For example, ethanol and propane have comparable molecular masses, but their boiling point differ widely. The boiling point of methoxymethane is intermediate of two boiling points. इथेनॉल मोलिकुलर मास बॉइलिंग पॉइंट कितना होता है 46 एंड 351 केल्विन. मिथॉक्सीमीथेन मोलिकुलर मास बॉइलिंग पॉइंट 46 to 48 केल्विन. प्रोपेन मोलिकुलर मास बॉइलिंग पॉइंट 44 and 231 केल्विन. The high boiling point of alcohols are mainly due to the presence of intermolecular hydrogen bonding in them, which is lacking in either in ethers and hydrocarbons. Solubility of alcohols and phenols in water is due to their ability to form hydrogen bond with water molecules as shown. The solubility decreases with increase in size of alkyl aryl hydrophobic groups. Several of the lower molecular mass of alcohols are miscible with water in all proportions. Chemical reactions. Alcohols are versatile compounds. They react both as nucleophile and electrophiles. The bond between OH is broken when alcohols react with nucleophiles. Alcohols as nucleophiles. ROH plus C gives out ROHC. R gives out ROC plus H positive. The bond between CO is broken when they react as electrophiles. Protonated alcohols react in this manner. Protonated alcohols as electrophiles. Based on the cleavage of OH and CO bonds, the reactions of alcohols phenols may be divided into two groups. Reaction involving cleavage of OH bond. Acidity of alcohols and phenols. First, reaction with metals. Alcohols and phenols react with active metals such as sodium, potassium and aluminium to yield corresponding alkoxides, phenoxides and hydrogen. In addition to this, phenols react with aqueous sodium hydroxide to form sodium phenoxide. The above reaction shows that alcohols and phenols are acidic in nature. In fact, alcohols and phenols are Bronsted acids, i.e. they can donate a proton to a stronger base. Second, acidity of alcohols. The acidic character of alcohols is due to the polar nature of OH bond. An electron releasing group CS3C2H5 increases electron density on oxygen, tending to decrease the polarity of OH bond. This decreases the acid strength. For this reason, the acid strength of alcohols decreases in the following order. प्राइमरी में सबसे ज़्यादा होती है, फिर सेकेंडरी में, फिर टर्शरी में. Alcohols are, however, weak acids than water. This can be illustrated by the reaction of water with an alkoxide. Base plus acid gives us conjugated acid and conjugated base. This reaction shows that water is a better proton donor, i.e. stronger acid than alcohols. Also in the above reaction, we note that an alkoxide ion is a better proton acceptor than hydroxide ion, which suggests that alkoxides are stronger bases. Sodium ethoxide is a stronger base than sodium hydroxide. Alcohols act as Bronsted bases as well. It is due to the presence of unshared electron pairs on oxygen, which makes them proton acceptors. Third, acidity of phenols. The reactions of phenols with metals, example sodium and aluminium, and sodium hydroxide indicates its acidic nature. The hydroxyl group in phenols is directly attached to the sp2 hybridized carbon of benzene ring, which act as an electron withdrawing group. Due to this, the charge distribution in phenol molecule as dissipated in its resonance structure causes the oxygen of OH group to be positive. The reaction of phenol with aqueous sodium hydroxide indicates that phenols are stronger acid than alcohols and water. Let us examine how a compound in which hydroxyl group attached to an aromatic ring is more acidic than the one in which hydroxyl group is attached to an alkyl group. The ionization of an alcohol and phenol takes place as follows. Due to higher electronegativity of sp2 hybridized carbon of phenol to which OH is attached, electron density decreases of oxygen. This increases the polarity of OH bonds and results in an increase in ionization of phenols than that of alcohols. Now let us examine the stabilities of alkoxide and phenoxide ions. In alkoxide ion, the negative charge is localized on oxygen, while in phenoxide ion, the charge is delocalized. The delocalization of negative charge structure 1 to 5 makes phenoxide ions more stable and favors the ionization of phenols. Although there is also charge delocalization in phenol, its resonance structure has charge separation due to which the phenol molecule is less stable than phenoxide. In substituted phenols, the presence of electron withdrawing groups such as nitro enhances the acidic strength of phenol. This effect is more pronounced when such a group is present at ortho and para position. It is due to the effective delocalization of negative charge in phenoxide ion when substituted is at cathode or para position. On the other hand, electron releasing groups such as alkyl groups in general do not favor the formation of phenoxide ion, resulting in decrease in acidic strength. Creosotes, for example, are less acidic than phenols. pK values of phenols and ethanols. Esterification. Alcohols and phenols react with carboxylic acid and acid chlorides and acid anhydrides to form esters. The reaction with carboxylic acid and acid anhydride is carried out in the presence of a small amount of concentrated sulfuric acid. The reaction is reversible and therefore water is removed as soon as it is formed. The reaction with acid chloride is carried out in the presence of a base. pyridine so as to neutralize HCl, which is formed during the reaction. It shifts the equilibrium to the right hand side. The introduction of acetyl CH3CO group in alcohols or phenol is known as acetylation. Acetylation of salicylic acid produces aspirin. B. Reactions involving cleavage of carbon oxygen bond in alcohols. The reaction involving cleavage of carbon oxygen bond takes place only in alcohols. Phenol show this type of reaction with zinc only. Reaction with hydrogen halides. Alcohols react with hydrogen halides to form alkyl halides. ROH plus HS gives out RX plus H2. The difference in reactivity of three class alcohols with HCl distinguishing them from one another. Lucas test. Alcohols were soluble in Lucas region, concentrated HCl and ZnCl2, while their halides are immiscible and produce turbidity in solution. In case of tertiary alcohols, turbidity is produced immediately as they form halides easily. Primary alcohols do not produce turbidity at room temperature. Second, reaction with phosphorus trihalides. Alcohols are converted to alkyl bromides by reaction with phosphorus tribromide. Dehydration. Alcohols undergo dehydration, removal of molecules of water to form alkenes on treating with protic acid. Example, concentrated H2SO4 or H3PO4 or catalysts such as anhydrous zinc chloride or alumina. Ethanol undergoes dehydration by heating it with concentrated H2SO4 H443 Kelvin. Secondary and tertiary alcohols are dehydrated under milder conditions. For example, CH3, CHO, CH3, 85% H3PO and 440 Kelvin under gives out CH3, CH double bond CH2 plus H2. Thus, the relative ease of dehydration of alcohols follows the following order. Tertiary में सबसे ज़्यादा, फिर secondary, फिर primary. The mechanism of dehydration of ethanol involves the following step. Mechanism. First, formation of protonated alcohol. Second, formation of carbocation. It is the slowest step and hence the rate determining step of reaction. Third, formation of ethene by elimination of proton. Thus, acid used in step 1 is released in step 3 to derive the equilibrium to the right. Ethene is removed as it's formed. Fourth, oxidation. Oxidation of alcohols involves the formation of a carbon-oxygen double bond with cleavage of an OH and CH bonds. Such a cleavage and formation of bonds occur in oxidation reaction. These are also known as dehydrogenation reactions, as these involve loss of dihydrogen from an alcohol molecule depending on the oxidizing agent used. A primary alcohol is oxidized to an aldehyde, which in turn is oxidized to a carboxylic acid. Strong oxidizing agents such as acidified potassium paramagnet are used for getting carboxylic acid for alcohols directly. CrO3 in anhydrous medium is used as oxidizing agent for isolation of aldehydes. RCH2H undergoes CrO3 gives out RCHO. A better reagent for oxidation of primary alcohols to aldehydes in good yields is pyridinium chlorochromate (PCC), a complex of chromium trioxide with pyridine and HCl. Secondary alcohols are oxidized to ketones by chromic anhydric CrO3. Tertiary alcohols do not undergo oxidation reaction under strong reaction conditions such as strong oxidizing agents KMnO4 and elevated temperatures. Cleavage of various CC bonds takes place and a mixture of carboxylic acid containing lesser number of carbon atoms is formed. When the vapors of a primary or secondary alcohols are passed over heated copper at 573 Kelvin, dehydrogenation takes place and an aldehyde or ketone is formed, while tertiary alcohols undergo dehydrogenation. C. Reaction of phenols. Following reactions are shown by phenols only. Electrophilic aromatic substitution. In phenols, the reactions takes place only on the aromatic ring or electrophilic substitution reaction. The OH group attached to the benzene ring activates it towards electrophilic substitution. Also, it directs the incoming group to ortho and para position in the ring, as these positions becomes electron rich due to the resonance effect caused by OH group. The resonance structure are shown under acidity of phenols. Common electrophilic aromatic substitution reactions takes place in phenols are as follows. First, nitration. With dilute nitric acid at low temperature 298 Kelvin, phenol yields a mixture of ortho and para nitrophenols. The ortho and para isomers can be separated by steam distillation. Ortho nitrophenols in steam volatile due to intermolecular hydrogen bonding, with para-nitrophenol is less volatile due to intermolecular hydrogen bonding, which causes the association of molecules. With concentrated nitric acid, phenol is converted to 2,4,6-trinitrophenol. The product is commonly known as picric acid. The yield of the reaction product is poor. Nowadays, picric acid is prepared by treating phenols first with concentrated sulfuric acid, which converts it to phenol 2,4-disulfonic acid, and then concentrated nitric acid to get 2,4,6-trinitrophenol. Can you write the equations of the reactions involved? Third, halogenation. On treating phenol with bromine, different reaction products are formed under different experimental conditions. A. When the reaction is carried out in the solvents of low polarity such as CHCl3 or CS2 at low temperature, monobromophenols are formed. The usual halogenation of benzene takes place in the presence of a Lewis acid such as FeBr, which polarizes the halogen molecule. In case of phenols, the polarization of bromine molecules takes place even in the absence of Lewis acid. It is due to the highly activating effect of OH group attached to the benzene ring. B. When the phenol is treated with bromine water, 2,4,6-tribromophenol is formed as precipitate. Second, Kolb's reaction. Phenoxide ion generated by treating phenol with sodium hydroxide is even more reactive than phenol towards electrophile aromatic substitution. Hence, it undergoes electrophile substitution with carbon dioxide. A weak electrophile, orthohydrobenzoic acid, is formed as the main reaction product. Reimer-Tiemann reaction. Third reaction है ये. On treating phenol with chloroform in the presence of sodium hydroxide, a CHO group is introduced at ortho position of benzene ring. The reaction is known as Reimer-Tiemann reaction. The intermediate substitute benzyl chloride is hydrolyzed in the presence of alkyl to produce salicylic aldehyde. Reaction of phenol with zinc dust. Phenol is converted to benzene on heating with zinc dust. Oxidation. Oxidation of phenol with chromic acid produces a conjugated diketone known as benzoquinone in the presence of air. Phenols are slowly oxidized to dark colored mixtures containing quinones. Some commercially important alcohols. Methanol and ethanol are among two most commercially important alcohols.